So our next talk is by Mr. Sagemiller, and it's about the lazy evaluation of infinite dimensional functional spaces with wavelet basis.
Hello, and thanks. Yeah. So those of you who know me, maybe from last year or from Stack Overflow, know that I like to rant about what could be called the MATLAB-infected way of thinking. And so I'm going to start with a couple of strong opinions, which you may disagree with. I'm going to say a vector is not an array of numbers. It's also not a monad or a representable or Neperian functor. I'm going to say, although there are, of course, vectors that are these, and they are interesting, but I'm going to say that first of all, we should think about a vector is just an element of some vector space. You should on the Haskell library for vector spaces by Conor Elliott. And it represents, of course, something that we want to do numerical commutations on. This is often some points in physical space, but it can in particular also be function spaces, or spaces of distribution of probabilities, stuff like that. Before I go into the ideas that we are going to propose for how this might perhaps be better done than with just arrays of numbers in the future, let me start out and consider why does it even make sense to use arrays. And because evidently it makes some sense, and yeah, you all know this. You can just, if you have some vector space, pick any basis vectors like that, and then you can take any third vector and just treat it as a superposition of these vectors. Can you see the arrows? Okay. Yeah, you all know this, and these basis vectors don't really need to be orthogonal. They can also be like this, and it still works. Maybe a bit more inefficient, but in principle we can, even if we have a non-orthogonal system, we can basically always just transform our entire space. So if I stretch this a bit in this direction over here, then it will eventually become orthogonal. And all this can be done with a couple of Gaussian eliminations, provided the vector space is finite dimensional. So in the finite dimensional space, you really can just pick any basis vectors and can always build an orthogonal system that's complete. Problem is that function spaces are inherently infinite dimensional. And this doesn't really work this way. I mean, it kind of works though. You can, the best example is the Fourier expansion, which essentially takes some function on, in this case I've pictured as the unit interval, and then expands it in trigonometric functions. Of course, you also know that. There are a couple of problems with this. For instance, if I use it for this, then you will see there starts to rise this Gibbs phenomenon, that at the boundaries it doesn't work very well. It starts to oscillate a lot. And also the Fourier basis is massively non-local, which is a problem for parallelization, and also if you're doing nonlinear simulations, then everything smears across the whole domain. So it is very good for some applications, but not really a good universal thing to always use. And it's heavily based on this orthonormal basis aspect as well. So basically, you take some basis and make it orthonormal, as we saw earlier with finite spaces. And yeah, in a Hilbert space, that's the general term. In this case, it's the L2 Hilbert space. So we're not really considering functions as pointwise evaluations, but only as integrals over them. I'll come a bit more to that later. So that kind of works, but if we just forget about all of that for a minute, we might actually think a function is kind of an array in a much simpler way, because if we just consider individual points, then we can also sort of build a function out of that. We might just use point evaluations at single points as our basis vectors. But this doesn't really work at all, because the real line is it's not only infinite, it's overcountably infinite. So if we zoom in sufficiently, then eventually we will come at some point where it's all zero. And so that's not really a way to do it. The way it can be done, it is actually what it kind of means when most people do arrays for functions is that we limit our resolution to something, so we don't take an infinitely sharp peak, but we take some kind of head function. This is basically the basis of finite element methods. And this way we can approximate the function quite well, although of course we are limited to the resolution that we take. So if I now want to resolve, for instance, this peak a bit better, then it can't really be done. Of course there are then adaptive mesh resolution approaches where you kind of fix it after the fact, but it's usually a bit ad hoc, and it would be kind of nice to formalize this in a bit more elegant way, what we're really trying to express mathematically. First, let's see why does it even make sense to consider a limited resolution. And this is basically because most functions we have in physics and also in many other applications where you do numerics are continuous functions, meaning that if you evaluate a bit further from the point you actually meant to, then the function will only change so much by some other small number. Continuous functions in particular, but also other functions, are often integrable. And yeah, that's kind of the idea behind these weak formalizations of PDEs, and I don't want to explain that, but so that you kind of represent the function value at some point by the average over a whole interval. It's not always just the average, that you may have some other kernel, but that's details which aren't important here. So anyways, the integral kind of gives a good overview if you're not so much interested in the finest details yet, but may be interested in them later. So if we take this to the extreme, we might just start out and represent the function globally as some constant, and then we just focus on the details in smaller parts of the domain. So the classical divide and conquer, this gives us some kind of tree data structure, and the way this is interpreted is then that, so we have in blue the function that we actually want to describe, but what we store is first this constant offset here, y0, which is in this case computed as an integral, so we average over the function, and then in each of the halves of the domain we take another function and then go recursively down. So if we zoom in here, then it will switch, then this is the function we're interested in, and so on. And eventually, if we zoom in on some very small piece, we will come up with something that's very close to 0, because we've already stored all the offsets in a higher level domain. Yeah, and we can then actually evaluate these functions pointwise. So if we store this data structure as the representation, then we can take some point where we want to evaluate it. By the way, D1 is supposed to be the one-dimensional unit disk, which is a bit of a strange name, but I just mean the interval from -1 to 1. So this is what I showed in the plots earlier. It's always this D1. It's the domain on which I consider these functions. And yeah, the way it works, we look, first we take our offset, that's kind of constant anyways, and then we look, are we on the left half? Then we evaluate the left half and add it to it, and then it's very simple. This doesn't work, of course, because you may have noticed this is an infinite tree. So actually, at some point we will need to terminate and set a kind of 0 value where it knows now it should stop, and then we just use 0 at this point. We can also add these strictness annotations to actually make sure that the tree will be finite and that this thing terminates. This is kind of optional, but yeah, you can do it. And then this is a perfectly safe function for evaluating this particular representation. What's a bit nasty here is that you see each of the left and right functions also will have this offset in between, but if we raise the offset in both of the halves, then we kind of meddle with this one. So in practice what we'll actually want to do is we only store the difference between the both offsets of the functions, and then these functions are by construction they have an integral of 0, and so no offset anymore. So what we're actually going to store here as the y field is going to be just the difference, and only on the very topmost level we are going to store a global offset. So if we show this again, we still, on the topmost level, we store this red line as the offset, but then we also immediately store the difference in offset between the two halves. You know, see this is a step function as I do it here. So basically I do an offset in the left half and the exact opposite offset in the right half. And if we then zoom in, then we already have 0 global offset in this half. So no integral here, no redundancy in the data structure. But apart from that, it works exactly the same way, and you can still zoom in and so on. If I zoom in a bit more, you see the functions I'm showing you are actually already represented in this format. So you see at the very low level, they are step functions. And this is basically these wavelets you see here. They are very established for decades, Haar wavelets in this case. So this is kind of the simplest localized integral-based base function that you can pick. And it's not very efficient. I said earlier, we want actually to describe continuous functions, but these are massively non-continuous. So this is some future work we would rather like to use better behaved local functions, but in principle it works, and it can still approximate continuous functions arbitrarily well. Now, this is all nice maybe on a conceptual level, but of course we also want to use it for some actual applications, and it's not really enough to just be able to represent these vectors. You also want to do some kind of, essentially linear algebra with them, which everyone does when they're doing signal processing in MATLAB, for instance. First of all, we need to, so if we have some kind of function given as a function, then we want to be able to represent it in this form. You might think, okay, we need all these integrals on every single interval. This is very inefficient, but actually it can be done quite simply because the integral is just additive on both halves. So we can recursively go down and first compute only the integral at the lowest levels. We could actually also use some heuristic here, how low we need to go in the trees at each level. So this is not really a problem, but what do we actually do with it then? And yeah, as I said, linear algebra is usually what you want to do with vectors. So linear mappings are essentially the objects of interest, and you may want to invert them or something. The kind of simplest linear mappings that you could consider is just mappings from the vector space V, I call it, to the scalars of this same vector space. So this is the space, the dual space of V. And that's also a vector space. We can just add functionals. U and V are in this case linear functions. And adding them amounts just to adding the result, kind of the obvious thing. But if you do it literally this way, then you're not going to get very far with any simulation or something, because if you add kind of thousands of these vectors and then try to evaluate them in the end, you need to go through all of them, and it's kind of the same problem we had earlier when we represented functions on the read line in the first place. We want something that can be stored, and we can actually do updates and not become slower and slower to the process. Fortunately, there is quite a good way to do this. Again, at least in the finite dimensional case, but also in the Hilbert space case, and that is the Ries representation theorem. So you can, if you want to represent some functional, so in the dual space, you can always represent it by just a normal vector in the space you originally had. And so mapping a vector, in this case phi is in V, to a dual vector is very simple. So the dual vector just takes another vector and calculates the scalar curve, which is somehow given in your Hilbert space. And the other way around is a bit more tricky, but it can also be done if it's a Hilbert space. And yeah, what this suggests is that you, instead of storing functionals as function, you can just store them as vectors in the same representation that you originally had. And in the finite dimensional case, again, this works. It's in MATLAB, they call it row vectors and column vectors. So the column vectors are usually the vectors and the row vectors are the, but it's confusing, everybody does it different. But in principle, that's what you're doing. One problem is, or maybe it's not a problem, it's kind of something that gives us to think about, is that some linear functionals can clearly not be represented as functions. And the classical example is this Dirac distribution that physicists use all the time, which can be seen in this way. We take some function on the interval, or on the real line, it doesn't make a difference, and we just give the number that is the function at 0. So this way the Dirac distribution is very simple to write down. We just take a function as the argument and evaluate at the place 0. But if we actually try to write this Dirac distribution as a function on the real line, then we end up with some scary thing which is 0 everywhere, but infinitely high at 0, which is not a function clearly, but physicists often pretend it is. Fortunately, we are not really constrained with our representation. I mean, we can just try it and use the same tree structure as we had before, and simply interpret it as the dual space. And because all these functions in there are supposed to be linear, we know that all this really can do is multiply the coefficients in the original data structure, so the one without all these co-prefixes. And yeah, we basically just look at both tree structures. By the way, this is supposed to be a co as well, and this is wrong. Okay, so at first we just take the top level offset and multiply it with the top level offset of the function we're applying it to, and then we recurse down and do essentially the same thing. But if either of the structures is 0 at any point, then we just terminate. So if we have a function that's constant in some domain, then we know we don't need to recurse down further. We just take the offset coefficient at that level and take it with whatever weight we want. Yeah, I've called this dot operator because it can be interpreted as a multiplication, but it can also be interpreted as just function application. If we say these cohort functions are functionals and supposed to just describe evaluating the function in some way. And if we do this, then we can, for instance, actually describe the Dirac distribution. It turns out this works. What we need is, you may have noticed that I omitted the strictness annotation at this point. So I don't require that Haar unbiased is actually of finite depth, which is okay because we know that Haar D1 will be finite length. So even if this is infinitely deep, then we can still evaluate this for any function on the real line and be perfectly safe that it will terminate. And this way, it turns out we can actually implement the Dirac, and we can even implement it in the general way. So we say we want a functional that implements integration over a subinterval of D1. And I haven't showed the code here, but it's not too difficult, it's just a bit wordy. And so a big class of functionals that are interesting in practice can be done just fine this way. So this is one thing that I find nice about this Haar, and kind of motivates that it's actually a good idea to make a type level distinction between a vector space and its dual space. But the more important thing is actually that this is kind of one ingredient to linear algebra, that we have the simplest type of linear functions, the scalar value of functions. But we want, in principle, to be able to describe general linear mappings between vector spaces. And for this, we also need tensor products. So I'm not sure if you don't know. I mean, this is not a Kronecker product right now, so this might be a bit confusing with the talk before. This is the tensor product between two vector spaces, and the tensor product is just defined to be a bilinear operation that essentially takes pairs of vectors as its basis, if you want to base, and then it's supposed to obey some laws. And in practice, what people usually do is they represent these as matrices. So, very simple form of that. If you want a matrix of finite dimensional vectors, in this case 2 by 2, then you can just represent it as a nested list, which is of course the same as just the list constructor applied 2 times in a row. So essentially you are composing the list functor. Now you may remember at the start of my talk I said I don't want functors as vectors. This is actually a bit contradicting to that. But it won't surprise most of you if you know Edward Kmet's linear library, for instance, or if you heard the talk by Jessic earlier, then So this is something you can do. You can represent, if you have, if you have then you can just represent the tensor product as a tensor product in the element. So essentially you're composing 2 functors. in this particular case it works, although I'm not sure if it's really the best representation, but I won't have time to go into that level of detail. You can then represent these linear functions, generally from a vector space V, or from the space of Haar-based functions on the real interval, to some other spaces as yeah, here it is actually, no, here. Yeah, you take the tensor product of these domains. So what you're essentially doing here, you're taking a function on the real line, and each point is supposed to be in another vector space, and the way you represent this is, no, what you want to represent with it is the tensor product. This is also well known in numerical techniques, that you often like this tensor product structure to actually get work done in higher dimensional domains. So, and this way you can then implement, for instance, the identity mapping, which I also showed already a couple of times. Now, it's perhaps a bit boring to be able to represent the identity mapping, because it's not clear that this can actually be done, because these spaces, after all, are infinite dimensional. So we kind of need an infinite by infinite dimensional matrix to represent this. And if you just try to enumerate one row of infinite times infinite, it's not going to work. Again, the way it works is because the Haar structure can be infinitely deep, and each of the entries in it will be just finitely depth. So, yeah, and we can write this down, and we can also confirm that it really implements the identity mapping. So that's kind of nice, and this also allows us to kind of memoize any sort of linear functions by f-mapping over this identity function. So that's kind of useful. Okay, so that's how far I am right now. Of course, there's much future work to be done. We want to be able not to just describe functions on the unit level, it's limiting. It's quite easy to extend it to functions of the whole real line by just stitching together a representation of that in some way. Then one really important thing for actually application is we want some higher order reconstruction. So you saw I'm right now using step functions, which are pretty bad if you want to represent continuous functions. So what you actually want to do in practice is more like you have the function you want to describe, and then you take some kind of head functions. Again, this is commonly done in finite elements methods already, and then you can do a similar thing that you just zoom that in and refine it ever more. And the functions are actually represented much more efficiently this way, if you do it right. But I haven't quite figured out how to do tensor products with this particular representation, so we are still working on that. Then we also want to avoid that, yeah, I said the tree can have different depth at different points, but it's no use if you just use the full depth everywhere the same. For instance, if you're trying to do some numerical simulation of fluid dynamics and you have a shock running through the system, it's no good if after the shock everything's finally resolved, although there's no structure there. So we want some kind of heuristics to avoid that the trees are deeper than we actually need them. Then these tensor products probably should be done in a bit different way as well, because for instance we can transpose a tensor of the current structure if it's infinitely deep in one dimension. It might be good to switch to some kind of Morton ordering, so that we basically use a KD3 across our domain. And then, of course, we want to use it for some actually numerical applications. One thing we have in mind right now is optimal transport, which is relevant for machine learning. And I would also be able to use this for partial differential equations. But for that, we probably first need to start with higher order reconstruction. Yeah. Okay, so that's thank you.
Thank you. Any questions?
Just a general question. Second presentation we heard about Chebyshev polynomials. I mean, your bases are basically linear, constant functions, step functions. Is there a point of using maybe polynomials?
Definitely, yeah. I mean, what you're usually doing in finite element methods, you switch to some kind of second order polynomial. It's not, I mean, at least for hyperbolic partial differential equation, it's not really useful to go to higher order polynomials, because becomes very expensive and you lose the locality. So if you have a very high expansion, then tweeting one point will tweet points somewhere completely different. So for parallelization, at least this is not good. And also in practice, it's kind of second order seems to be the sweet spot for many applications. But definitely, polynomials are a good idea. And of course, higher order polynomials can be very useful for specific applications as well, when you don't want locality. But at least for the stuff I'm interested, I think second order is what we're going to aim for. Mm-hmm. But zeroth order, what we have here, is definitely too low, yeah. Right.
Any other questions?
You mentioned there's possible applications in machine learning. Could you say a bit more about that?
Yeah. So this optimal transport is basically what it's supposed to describe is a mapping between two probability distributions. And probability distributions are the things that they can be actually point-wise, so they can kind of be Dirac distributions. And so it's conceptually interesting if the right way to do it is to consider it as a mapping not between functions on the real line, as probability distribution on the real line, but actually dual vectors on these functions. And we have tried some stuff and it doesn't really work, but it looks that it actually at least works better with the dual vectors than it does with the vectors, but it should actually work with the vectors as well right now. So this is not, but this is one idea which, and this optimal transport is kind of conceptually the way you want to do interpolation on many types of data. I mean, you can of course smear them out, smear the data out, and then you can just do point-wise interpolation, but this optimal transport seems to be kind of a conceptually better way for many of these applications, but of course there are many approaches there, just one idea.
So you mentioned that sort of direct delta, you could make it work.
Yeah.
To what extent is that just sort of a trick that happens to work there versus, like, does it actually work for all distributions, or, you know, sufficiently smooth?
I'm not sure how to prove that it could work for all distributions. Probably it doesn't. I mean,
have you considered taking it in that direction?
Trying to write down a proof that it would work for any distribution. I really don't know how to start this. Might be interesting though, yeah.
I mean, I just use like method of line. For the PDE, I just say I'll see the method of line. Have you got some idea? Do you think this is going to be better somehow?
I mean, if we're going to use this for PDEs, then for hyperbolic PDEs, I'm not sure if this is really, it's probably not as good as some good Lagrangian solvers and this kind of stuff and method of lines. So probably for many domains you still want something more domain specific. This is kind of a very general formalization that would be a good starting point for some applications. Yeah. It's probably not the best thing for everything.
Yeah. Okay.
Okay, thank you very much.